Hello everybody, today I'll talk about chapter 6 and this is about amplifier concepts in semiconductors, and this is a very simple and easy chapter. So let us go through the chapter. It's just objectives. Okay, let us define what's the meaning of signal amplification first. Signal amplification is that it means that you amplify the signal, posting signal level from a sensor or driving loads like, for example, speakers or antennas. So you want to increase the amplitude of the signals. The amplifier multiplies the amplitude of the input signal by a constant value without changing its frequency or shape. It's supposed to be like this, of course. And the amplifier is described in terms of its amplification factor. So what is the ratio between voltage, input voltage and output voltage, or input power and output power, or input current and output current, and the input and output impedances. So these are the three main parameters in any amplifier: the input impedance, the output impedance, and the amplification factor. The amplification factor is called the gain. It's expressed in terms of voltage, current, power gain. Other items of interest include the maximum output level of compliance, useful frequency range, noise, distortion, and so on. So this is some stuff that also, if you design amplifier, you need to study this. When you design amplifier, for example, you cannot amplify unlimitedly. You have to have a limit, okay, for the input signal. If the amplification is 10, for example, then in this case, the input signal could be, for example, for up to 1 volt, 0.5 volt, for example, depending on the circuit of the amplifier. This is what we call it compliance, because if you increase the voltage or the input voltage, in this case, the output will be trimmed. This is exactly like when we have an operation amplifier in circuits. You have the input and output voltage. The voltage, DC voltage, is, for example, positive 15, negative 15. Then you cannot exceed this voltage. If you have the output signal is 100 and negative 100, for example, it will be clipped at 15 and negative 15. And you don't want to do that, unless, of course, you do it in purpose. Like, for example, like if you want to generate a square wave, for example, then you know that you will get a square wave by clipping the signal. You want to study also the noise. You don't want to have some noise to distort the signal, and so on. Also, the frequency range. Not all amplifiers will work at all frequencies. There is a frequency range where this amplifier is working in. For example, from 10 kilohertz to 10 megahertz, for example. Before that and after that, no, it will not work. Every amplifier has a certain frequency that will work. Okay, before that and after that, it may not work. This is just a simple amplifier model where we have something look like operation amplifier. This is the input voltage, and we have a ZN, and then we have a source here that is AV. AV is the amplification, which is the V out over Vn, and you have the out. So these are the three parameters: the input impedance, the output impedance, and the amplification AV. Then it is the ratio between output and input voltage. Okay, so you can model the amplifier using this simple one here. It's just an input impedance, output impedance, and the source, like this, AV times Vn. So in this case, V out equal what? V out equal, because you do not have current here, it will be AV times Vn, because you don't have current in the out. This is the unloaded one. There's no, is this written here? No, this is unloaded one. You don't have a load. There's no RL, for example, or ZL. You do not have an input source with source impedance. But if we have it like this is what we call it loading effect. In here we have a generator, and this generator has internal impedance, generator, or sometimes it is just resistance. And you have a load, RL. You want to deliver the power or voltage to a certain load. So now what is the voltage here, the relation between this V out and this V generation, V input or V generator here? How can we do that? You can use this circuit here, this one here, a simple circuit. And what is the output voltage here? This is the output voltage, is the voltage across the L. So you can use a voltage divider because you have this source is divided between two resistors, two impedances. Okay, so what is the voltage here? The voltage here will be Z load divided by Z out plus Z load, these two resistors, okay, multiplied by the source. And the source is AV time VN amplifier, which is this one here, this part here. This is the model which we just talked about. We talked about it in the previous slide. Okay, so AV times this one here. Okay, so now this is the V load. V load, so let me write it here. So V load equal what? Or V out, in this case, equal what? Equal ZL, Z load, divided by ZL plus Z out. What times the voltage? The voltage here is what? The voltage is AV time VN amplifier. Okay. Then after that, we look at VN amplifier. What's VN amplifier? Is this voltage here, this circuit, this part. It is the output voltage of the source here. This is the voltage across Zn. Then we can reuse a voltage divider again to calculate VN amplifier, which is what? It is Zn over Zn plus Z generator plus Z generator okay, time what? Times the voltage, which is V generator. V generator. And then we substitute by this here in this equation. Go back here. Then we will get this equation here. Okay, so V out or V load equal what? Equal ZL divided by ZL plus Z out, or Z load over ZL load plus Z out, time what? Time this Zn time AV time Zn over Zn plus Z generator time V generator. Of course, if you want to get the ratio between V out, this V out, and V generator, the last output voltage and the first input voltage, the source, then it will be this number, this value here, this one here. Okay, and we call this A system. This is the amplification for the system. Of course, if Zn is much larger than Z generator, which is usually like this, Zn is designed to be high, so it will be much higher than Z generator, and Z load is much larger than Z out. So usually we need to design amplifier so that Z out is small. So this one is small, and this one is large. Oh, come on, large. Okay. And this is what happened in amplifier, operation amplifier. In operation amplifier, if you remember, the input impedance is infinity, ideally is infinity, and the output impedance is 0. Okay, and if this is the case, then in this case, A system will be the same like AV. But if it is not, then in this case, E system will be less than AV because of the loading effects. So let us calculate this one, for example, here. AV equal 20, and Z out is 200. Zn is 10K, Z generator is 600, Z load is 1K. Then if I want to calculate a system and compare it with AV, let's see if it is close to 20 or not. Okay, so it will be V load divided by V generator, or just substitute in the previous equation. Zn is 10K, so it's 10K. Okay, so you calculate it here, 10K divided by 10K plus 600, which is 0.6K. So time AV is 20, so it's 20 time Z load, which is what's Z load, 1K, so time 1 divided by Z load, which is 1K, plus Z out, which is 200, which is 0.2K. So now, what is the amplification? 15.7. So we lost here 4.3 because of the loading. Why? Because it's not a perfect amplifier, because the input impedance is not large enough and the output is not small enough. If you imagine that this one is very close to number, for example, assume that, let us change these numbers here. Okay, let's assume that change. Okay, let's make this, for example, only, for example, 1 ohm. And this one here is, for example, 10 mega. Okay, let's see. What is the value of the amplification? If this is 10 mega and this is 1 ohm, then in this case, the amplification is what? Zn is 10 mega. So 10 mega, 10 million, divided by 10 million plus 600 equal, multiplied by AV, which is 20, multiplied by Z load, which is 1K, so this is 1000, divided by 1K, which is 1000, plus Z out, which is 1. Okay. Now, what is the amplification? Is 19.9788, which is almost 20. Then this one is a good amplifier. Now let's see what's next. Compliance and distortion. So as I mentioned before, if you design amplifier, you have to make sure that you will not have a clipping unless you do this in purpose. Okay, so here, for example, if this is the Q point, okay, so now you don't want this signal here to reach this value or to be more than this value, because if the if the current I'm sorry, if the current exceeds this value, it will be clipped. Same here, the voltage VCE, if the VCE level exceeds this value here, the cutoff, it will be clipped. So you don't want that, it will be distorted. So let's see, for example like this. This is one of the examples that I believe this is one of the problems that we have solved in or homework of chapter. This chapter, I believe chapter 4 maybe, or 5. I can't remember exactly. Okay, so here, let us see the value here. VCE was calculated to be this number here, 2.12 minus 2.44 Vs. And IC is calculated to be this one here. Okay. When you look at this transistor, the Q point for VCE is 2.12, and IC is 3.22. Okay, this without any source. Then in this case, when you add this Vs, if you have only 6 volt, so these are the numbers. This is a Q point. Okay, so now this is the load line. it's very clear that this point here is close to 3.75. It's far away from 0, of course. 3.22 is more close to 3.75 than 0. Same for 2.12. 2.12 is close to 0 more than 15. So this is supposed to be here, for example. I believe it should be here somewhere. Okay, so now in this case, this is the maximum level of IC. If you have an AC signal, then the maximum level is 3.75 minus 3.22. This is the maximum. Cannot be more than that. If it is more than that, then in this case it will not work. Same for the voltage here. The voltage cannot exceed the AC voltage, output voltage cannot exceed 2.12. Otherwise, it will not work. It will be clipped. Okay. Compliance and distortion here. When you clip a signal, this means that you create a different signal, because if you have a sine wave, this is a sine wave. A sine wave has only one frequency, because if you have 10, for example, sine 2 by 1000 t, then the frequency is 1000. This is the sine and cosine have only one frequency. But if you have a square wave, or if you have a sine wave that's clipped, no, this is not. It doesn't have only one frequency. This is equivalent to unlimited number of sine waves with different frequencies. So the signal will contain a lot of frequencies. So when you do clipping, you have the signal with a lot of frequencies. Okay, so this is a problem here. And each frequency for the operation of the amplifier will react separately, differently for each frequency. So for example, at this frequency, it will give you amplification 10. For the other frequency, maybe it is 8. The other frequency, maybe 7, and so on. So this is a problem when you have this distortion here. Besides, of course, that you create a different shape.